Hello, this is Daijun Hu from Department of Mechanical Engineering, and I'm a PhD student in National University of Singapore. Today, I'm going to share our work called Crystal Plasticity Model for Microscale Residual Stress Simulation in Additive Manufacturing. So during additive manufacturing process, especially we are working on laser powder bed fusion here, there is repeated and rapid heating cooling cycles and very large temperature gradients. So this complicated thermal history will induce complex tension and compression in material. There will be residual stress formed due to the inhomogeneous deformation, and as a challenge for the AM community, the residual stress can lead to distortion, warpage, and even cracks in AM parts. So it's very critical to understand, to predict, and even reduce the residual stress. So to the typical classification of residual stress, there are three types. Type 1 is macro scale, which is averaged at part scale. And type 2 is we are working on at grain scale, so called micro scale residual stress. And type 3 is atomic scale, such as dislocations. For type 2, experimental works often focus on several grains or a certain region of grains on surface. So simulation has its own advantage to provide a much larger, deeper picture at individual grain scales. So however, there are some difficulties for simulation of AM parts. For example, the molten pool evolution should be captured accurately by complex thermal fluid flow simulations. And anisotropy, the plasticity of grains, should be taken into consideration at this scale. So we are aiming at simulating this. And microscale residual stress of AM parts has been studied by previous works and can be revealed by the tension compression asymmetry in the mechanical behaviors and the residual lattice strain during the in-situ X-ray diffraction tests. So we will take these as references to establish and validate our model. This is the flowchart of our computational framework. Firstly, we get temperature profiles of LPBF processed by thermal fluid flow simulation and then applied to the phase field model for grain growth. Then we use a crystal plasticity finite element model to simulate the residual stress with the obtained temperature profiles and grain structures. So we can move on for more analysis. So this shows how the temperature profiles transfer in our framework. After running the CFD simulation, we select the region around the molten pool as a representative domain and do the interpolation at time scale of temperature. Then we import the data to CPFEM model to reproduce the laser scanning. So by this way, we can get the thermal stress in this domain. This is a material model, which is crystal plasticity based and can describe the thermomechanical response. So to fit the temperature change in AM process, we introduce the thermal eigenstring, the temperature dependency of the CRSS, and elasticity. So also to simulate the surge stiffness change due to the phase transformation during the process, we use residual stiffness method and use estimated residual coefficient for liquid and gas phase. We use three-step simulations to get the final residual stress in the simulation domain. First is to impose the temperature field from CFD simulation and get the thermal stress. We only release the top surface here and block others. Second step is relaxation, which favors the self-stress balance at room temperature. At last, we perform tensile loading along the laser scanning direction and extract the lattice strain for analysis. So after building the simulation chain, we use two experimental cases for model validation. The material is 316L stainless steel by LPBF. And in both experimental works, well, they have different process parameters, the residual lattice string and their evolutions of 4 representative green families are compared with our simulated results. So first, we need to calibrate the CPFEM parameters, including the critical result shear stress and hardening behaviors. We calibrate the 2 cases by their experimental stress strain curves respectively and use this calibrated value for subsequent simulations. One thing to mention is that the difference of the CISS comes from the different thermal history by different process parameters, because we set the CISS temperature dependent. So it's reasonable here. And then we get the lattice string results. First look at case 1. The dashed lines are simulated results and solid lines are experimental. Different colors represent different green families. First point to check is the residual lattice string at 0 applied stress, which reveals the residual stress remained in the samples. And then we find the error is very small along loading direction. It's a bit larger along the transverse direction, but still acceptable. Second is to check the lattice string evolution. We can find the linear and nonlinear behaviors can be reproduced accurately for most green families. The various lattice string evolutions can also demonstrate the anisotropic properties of this material. So also the simulation result of case 2 looks fine. The trend is similar and the error is small. So overall, we validated this model by comparing lattice string results. We find the residual lattice string is small. The evolution can be reproduced by our models with acceptable error, and the slope changes of the curves after yielding same trend. So namely, the plastic behaviors are reproduced. Therefore, the model is validated by these 2 cases. Then we just turn to the plastic deformation results. 3 representative moments are selected when laser at the center, when laser exits the volume, and when cooling stage finishes. So when laser enters, for most part, compression is induced here, the blue region, and after laser pass, the molten pool becomes shallow here, and tensile stresses are imposed, especially along the Z direction. It's obvious here. So we can find the tension region shape resembles the molten pool shape as a vertical strip in case 1 and the oval region in case 2. So this distribution also allows the patterns of the elongate grains. So the difference between 2 cases should be attributed by the process parameters. In case 1, the laser scan is slow, and laser scan passes slowly, and the power is larger. So the heat affected zone is larger, and the cooling stage is also longer. We find the deformation decrease more and become more uniform on the plane by this in case 1. So to further find the reason for the plastic deformation decrease, we select the YZ plane and draw the green boundaries here for the elongated grains. To check the plastic deformation evolution during cooling, the grains which has take case 2 as an example, which has less tension. We find the plastic deformation become more uniform from here to here after cooling stage. So the grains which has less tension can accommodate deformation from neighboring grains. For example, the deformation in green 1 is redistributed to green 2 and 3. And similarly, green 4 can accommodate the plastic deformation from green 5 and 6. For green 7 to 9, it remains a high deformation region after cooling, but still have a decrease. I think this may be caused by the green along direction, which is perpendicular to this plane. This redistribution mechanism can explain the residual stress partial decrease in cooling stage. So similar mechanism can be found in case 1. Deformation is redistributed to surrounding grains, which have less plastic deformation. We can find the whole picture also becomes more uniform, and high deformation transfer from grain 1 and 2 to 3 and 4, from 8 and 9 to 10 and 11, from 6 and 7 to grain 5. So the more uniform plastic deformation distribution than case 2 of case 1 than case 2 indicates that lower scan speed and longer cooling can favor the redistribution progress. So then if we look at the residual stress components on the plane, we can find the distribution is correlated with the shape of mountain pool with the green morphology and concentrates on elongated grains and resembles the shape of mountain pool. So this is much more obvious in case 2, because in case 1, as I have mentioned, the plastic deformation redistribution is longer, has longer time in cooling stage. So the redistribution works more in the laser track region in case 1. So also the predicted value here is reasonable compared with the experimental results. So at micro scale, it may be locally higher to reveal the deviation from grain to grain from the macro scale residual stress, which is average. So we find stress components sigma XX and sigma YY, and sigma ZZ are higher than sigma YY. So this stress orientation or direction may induce macro cracks in certain directions, such as perpendicular to the laser scan direction. So maybe we can tailor the residual stress by changing process parameters. Therefore, we can adjust the stress directions, so we can reduce the macro cracks. So here is a final summary conclusion here. We develop a computational framework to simulate the macro-scale residual stress of AM parts. In this work, we work on 2 cases of 316L steel by laser powder bed fusion. So first we calibrate the model by their stress strain curves, and then we validate our model by lattice strain results. So by this simulation, it provides insights on the formation, evolution, and distribution of residual stress in AM parts at individual grain scales. The formation caused by the mixture and the change of tension and compression is shown clearly, and distribution is correlated with the shape of molten pool and the grain morphology. So also by cutting a plane in the center, we can find the plastic deformation redistribution between neighboring grains during the cooling stage. So this may provide a new insights to study and adjust the residual stress, the micro-scale residual stress for additive manufacturing in the future. So that's all for my presentation. Thank you for listening, and any suggestion is welcome here. Thank you.